Now we are going to start the last talk of today, and it's my pleasure to introduce Carolina Benedetti from the Universidad de los Andes in Colombia, and Carolina will talk about lattice path matrix subdivision of the permutahedron. Okay, please, Carolina.
Okay, so thank you very much to the organizers, to Anna in particular for inviting me here, to all of you to stick to my talk. I am not an algebraic geometer. I do not do tropical geometry nor number theory, but I guess that what got me a spot here is that I like matrix. And I want to share with you some of the stuff I've been interested on for the last couple of years. And I'll tell you the relation with tropical geometry. Okay, so yeah, so this is an overview of what I want to tell you about. So on the upper right corner, here we have, so this is a polytope, a nice polytope that is given by the convex Hall of permutations on the set 1 up to n. That's known as the permutahedron. And this permutahedron has been cut out by two planes. I have drawn them. Here is a purple one and a kind of yellowish one. And that cutting out by planes have subdivided my permutahedron, my polytope, into pieces. Each piece will show you what is labeled with. It's labeled with a sequence of matrices that happen to be a quotient of matrices. But right away, the connection with tropical geometry is that this subdivision of the permutahedron is regular. And I guess you are used to the terminology coherent subdivision. So it's a subdivision that arises by giving weights to the vertices. And actually, in this case, this subdivision is given by putting some weights. And this weight vector is an element on the positive tropical flag variety. Anyway, so that's what the point I want to convey here, okay? Okay, so sure, we already are familiar with matrices at this point, but basically, the matrices I want to tell you about are the ones that are known as lattice path matrices. So lattice path matrices are part of the work of Bonin, Demir, and Noy from 2002, but also I found out that they appear in early work of Stanley from 76. So let me give you a pictorial way of describing them. So I will define them by example. So I'm going to fix my ground set to be the set 1 up to 19. So that's my n. And I'm going to build a lattice path matrix of rank 8. So how am I going to do that? I fix already my ground set. And the rank 8 tells me, so just draw a grid with 8 north steps. And then just go from the origin up to this corner. So this corner has coordinates 11, 8. Okay? So what I'll do is to build my lattice path matrix is I'm going to start fixing 2 lattice paths from the origin to the corner 11, 8. And with those 2 paths, I will build my whole matrix. So in this case, I'm going to fix this path, this purple path, and this is going to be one of the bases of my matrix. So the basis they will correspond to is the labels of every time I go north. So since I'm using in total 19 steps, I care about the times I go north. And the times I go north are my labels. In the first, the fourth, the fifth, seventh, blah, blah. So those are my north steps. And that sequence of north steps is one of the bases of my matrix of rank 8. And here I fix another one, and I call it L, which also, by the same principle, is I care about the collection, the labels of the north steps. So with my path U and my path L, so U for like upper, because visually is above the L1, L by lower, because visually is below. So I will build a matrix by saying that any 8 tuple of the set 1 up to 19 will be a basis if graphically that basis is in between my upper and my lower path, okay? Another way to describe it is I will construct my whole matrix by saying that the basis will be collections of subsets of size 8 out of my ground set that when you grab the labels of the north step, the labels of the B sequence are in between U and L. That's what I'm doing, okay? So graphically, that's a lattice path matrix, yeah. So U and L could intersect in a corner, but they do not, U does not overpass L, okay? Okay, so those are the matrices I will carry on throughout my talk, okay? And so I'm gonna do everything over the reals because I will care about positivity. And so I will stick to representable matrix here. So just a quick reminder is that I'm going to consider the real Grassmannian Kn, which is K-planes in n space. And so we know that every time we have a K-plane in n space, I can fix a basis, I can choose a basis. And out of that basis, I build a matrix, a full rank matrix. And that matrix will give me a corresponding matrix. And my representable matrix arise this way. So in particular, lattice path matrices are representable. So for instance, here I have the lattice path matrix with U path 1 to 4 and L path 4, 5, 6. And that corresponds to a rank 3 matrix with 6 columns where the stars are just generic elements. And if you are familiar with the terminology, lattice path matrices are actually generic points in the Richardson cell decomposition of the Grassmannian. That's actually how the paper of Stanley introduces them. Okay, but we can stick to the combinatorial picture. That's good enough for me. Okay, so as I told you, I'm interested in non-negativity. So out of the world of representable matrix, there is this family, this proper family, that arises by imposing non-negativity conditions. So in K-planes, or points in the Grassmannian, I'm going to look at points for which there is a non-negative representation. And what that means is, if I have a K-plane, I will ask myself if I'm able to come up with a matrix that represents it in such a way that all the maximal minors are non-negative, okay? And that's basically what a positroid is. So we, or at least someone like me that is more combinatorial than anything else, found about positroids from Postnikov's definition and several equivalences, but they also show up in earlier work of Bloom, where he calls them order sortable matrices. So it's equivalent to the current definitions of what we know as positroids. But basically, we can think of them just as representable matrices for which there exists a matrix that represents it with non-negative maximal minors. That's it, okay? So for instance, here I have a matrix on set 1 up to 4 of rank 2. And I ask myself, is this matrix a positroid? So I can think of this matrix as represented by a matrix that looks like this after row reduction. And so one just asks oneself if I can put here A and B in such a way that the basis of this matrix here correspond to the basis of this matrix here. And in this case, the answer is yes. I can just choose A to be positive and B as well. And I'm going to get a matrix realization of the matrix M. It means that this matrix is a positroid. On the other hand, if I consider again this matrix also of rank 2 on the set 1 up to 4, one can check that actually this matrix, although representable, is not a positroid. And it doesn't matter how hard one tries, one will not be able to find here A and B, so that the maximal minors corresponding to 1, 2, 1, 4, 2, 3, 2, 4 are strictly positive, and the other ones are 0. It's not possible. Okay. So one, say, definition that also Alex gave us to think of a matroid is in terms of matroid-based polytope. So just reminding us what that means is that we have a matroid given in terms of its basis, and we just take the convex hull of the indicator vectors of the basis. That gives us a polytope. And so Gelfand-Gorevsky, McPherson, Serkanova actually told us that that's an equivalent way of defining a matroid. And so certainly uniform matroids are the uniform matroid Kn is the matroid that contains all the matroids of a given rank inside, built out of a set of n elements. And actually they happen to be also lattice path matroids. And so for instance here we have the uniform matroid of rank 1 out of the set 1 up to 4, and this is a pictorial representation of its polytope. And here we have the uniform matroid to 4, and also its matroid polytope here. And so what I just said means that, for instance, if I take another lattice path matroid in particular of rank 2 on the set 1 up to 4, its matroid polytope will be contained inside this one. And if you see, the only thing I'm missing here is the basis 1, 2. So it means I just need to get rid of the vertex 1, 2 in this hypersimplex, and that's what I'm left with. Okay? Okay. Okay. So another way of saying what matroids are from the polytopal point of view is that they are 0, 1 polytopes that are generalized permutahedra. And this just means that their edges are in the right direction, so in the directions of the vector Ci minus Ej. And okay, so from this point of view, one may ask, okay, I have this nice family of matroids that are positroids, and so their combinatorics is super rich. Like, there are a lot of equivalent ways of describing them, purely combinatorial, forgetting that they are representable, and you can forget that you, or if you want to build a positroid, you do not need to come up with a matrix realization with positive maximal minors. You can focus on the combinatorics. And because the combinatorics is so rich, one may ask oneself, is there a way of describing positroids from the polytopal point of view? And so the answer is yes. This is a very nice theorem by Frederico, Felipe Rincon, Lorem, and I understand that Lam and Posnikov also came up with it. And basically, one can distinguish positroids by saying they have to be, of course, matroid polytopes. They are 0, 1 polytopes that are generalized permutahedra, but also they are alcoved. And this alcove condition just means that the H description looks like this. So it's like summing sequences, consecutive sequences of the variables and bounding them. So it's a very nice description of the polytope. And in particular, that's one way of proving that LPMs are positroids. So Nauer, Martinez, and Ramirez proved or gave an H description of LPMs. And this H description, you see that is basically telling you if you sum consecutive coordinates, they are bounded. So that's a proof that LPMs are positroids. Okay. So let me tell you a little bit about the combinatorics of positroids, because what I want to focus on next is a way of thinking of positroids on a given ground set, just combinatorially. So one thing you can do is every time you have a matroid, whatever your matroid is, you can construct out of a matroid a sequence of n elements such that each element is a k subset, where k is the rank of the matroid. How do you do that? So basically what you are going to do is you are going to take the smallest bases with the order on the ground set where 1 is less than 2, less than n. So that's I1. Then you are going to take for I2 the smallest bases, but with the order that tells you that 2 is less than 3, less than 4, less than n, less than 1, and so on. So with that cyclic shift of the usual order 1 up to n, you can build a sequence of n elements. Each one of those elements is a basis. There may be repetitions, doesn't matter. But basically, if you build that sequence of bases of a matrix, you can then tell out of this sequence when your matrix is a positrate by doing the following. Once you construct your Grassmann necklace, which is that sequence I just described, then you just take all the subsets of size k that are bigger than or equal to each one of them in the appropriate order. And you are going to get a bunch of stuff. You take all these k sequences and compare them one by one with each one of them. And when you take all that stuff that happen to be bigger than or equal to each one of the I sub j's, then one of two things may happen. Either the bases of your original matrix are properly contained in here, in that big collection you just built, or not. So when that big collection you just built happen to coincide with the collection of bases of your matrix, then your matrix is a positrate. So as an example here, say you have a matrix whose basis set is this, and then you are going to build I1, I2, I3, and 4. I1, you build it according to the order in 1, 2, 3, 4, and so on. So the smallest basis according to the first order is 1, 3, and the smallest according to the second order is 2, 3, and so on. Then what you ask yourself is, okay, out of the subsets of size 2 of my set 1, 2, 3, and 4, which ones happen to be bigger than or equal to 1, 3, 2, 3, 3, 1, and 4, 1? And the ones that happen to be bigger than or equal to them, you just throw in them. And in this case, when you do that, you can check that, for instance, 2, 4 is bigger than or equal to each one of them, and that's it. So in this case, your matrix is a positrate. So one way of describing positrates is by, or one way of labeling positrates is by this sequence here that I'm calling Grassmann necklaces, although I'm not defining them properly. But another way, which is a more combinatorial way, perhaps, is by constructing something called decorated permutation. And the decorated permutation is just a permutation that you assign to your positrate. And you can think of a decorated permutation just a usual permutation. It's just that your fixed points have one decoration out of two. Either they are decorated with an overline or with an underline, and that just means you have a loop or a co-loop. And there is a proper way of defining them. But basically, the point here is that if you fix your ground set, 1 up to 4, say, and you write down all the decorated permutations, there is a bijective correspondence between decorated permutations and positrates built on the set 1 up to 4. So, so here there is a picture of all the decorated permutations on the set 1 up to 3. And each one of those correspond to a positrate on the set 1 up to 3. And we'll make sense of this poset soon. OK. So the way we are going to make sense of this poset is we will order matrix. So these are matrices on the same positrates on the same ground set in particular. We could do it with matrices too, but in this case with positrates. We're going to order them with a partial order set structure. And that's going to come from the notion of flag matrix. So there are, as for matrix, there are a big amount of ways to define what a flag matrix is. One way of defining what a flag matrix is using circuits, so minimally dependent sets. So let me give you here an example. So let's take here the matrix obtained from this matrix M, and let's take the circuits of this matrix. So these are all the circuits. So for instance, the columns 1, 3, 4, and 6 have determinant 0. But if you remove any of them, you are going to have non-zero determinant. And let me just take out of this matrix the top 2 rows. So the top 2 rows will give you another matrix. And that's going to be a matrix of rank less. And what happens, or the relation that is between these 2 matrices, is that each circuit of the one of the bigger rank, each circuit here is going to be a union of circuits from the one below. And that's one way of defining what flag matrices are. So one definition is saying that if you have 2 matrices on the same ground set, you can say that, in this case, N is a quotient of M if every circuit of the big one is union of circuits in the small one. And when you have that a matrix is a quotient of another, that's just saying that those 2 matrices form a flag matrix. Okay? And as I said, there are lots of ways of thinking of them. So one question is, as I told you, like when you work with positrons, you realize of the rich combinatorics that they have. And one may wonder if you can determine, given 2 positrons using their combinatorics, when one is a quotient of the other. So this poset here is a way that I found could help to answer this question. So basically here, the poset has elements, all positrons on a given ground set. And a positron is less than or equal to another if that smaller rank one is a quotient of the other. So here the relation is just quotient, okay? And so if you think about it for a moment, so what I'm saying basically here is if you were to take a maximal chain in this poset, that means you are taking a sequence of positrons from rank 0, 1, 2, 3, up to n. And that maximal chain is telling you that each positron is a quotient of the next one. And what that means is that you are taking a flag, a full flag of positrons in this case. So in this work with Anastasia Chavez and Daniel Tamayo, we did some characterization of quotients of the uniform matrix using the combinatorics on the decorated permutations. And the operation we use to determine quotients of uniform matrix use some cyclic shift on the decorated permutation, and that cyclic shift operation actually happened to show up in later work by Parisi et al. Related to tilings of the amplituhedron, M equal to amplituhedron. Okay, so later on, a problem that I've been interested on for a while, whose answer I have not found, is certainly if you have 2 positrons on the same ground set, you can just determine whether one is a quotient of the other by one of the definitions. But something I do not know yet is, can you actually, if you have a positron of rank M and a positron of rank L on the same ground set, can you actually, so that one is a quotient of the other, can you make that relation saturate? So can you just fill the gaps so that you get a chain of positrons whose rank differ just by 1, step by step, and you have a quotient of the other? So I don't know the answer for that yet. For matrix, that is known. It's done with Higgs lift. But with positrons, I don't know. So because of that, so I wonder if for subfamilies of positrons that could be done. And so one of the results I have with Kolyak-Naua is that if you give me any lattice path matrix, on one hand, we can construct very easily all the quotients of a lattice path matrix that are lattice path matrix, and that I want to show you by an example. Yes?
Question to this problem. If you have quotient of positroids, and let's say then m, can you lift this to the reals? So can you find representations of n and m of the real numbers such that you get subvector space?
Yeah, so I guess your question is, if I have two positroids, one quotient of another, can I realize them by the same vector space?
And the linear I mean, you can both realize over the real numbers, right? But because it's positroid, and the question is if you can do it in a way that one vector space.
Yeah, the answer is no, not always. You cannot always do that. So yes, certainly each of them is representable, but it's not always the case that you can find, let's say, a common representation of them. Yeah.
Do you know if you have in your mind this one?
I can tell you where an example lies. Yeah. Okay. So, okay, yes. So here we have this LPM, and basically our characterization tells you that, okay, let me show you this example. Oops. Okay, here. So I want to build a lattice path matrix of rank 1 less that is a quotient of this. So to do that, what I'll do is I'll choose any of the labels of the purple path, any that I want. So say in this case I choose 11. Because I want an LPM of rank 1 less, what I need to do is have a new upper path that has length 1 that less than 1 less than this one. So the choice I'm making is because what I'll do is I will then forget about that being a north step in my new one. So I make my choice, and then I need to choose somebody in the green path to delete along with it. And the deletion of those two north steps, the purple and the green, will become a quotient. Once I choose the purple one, I have restrictions on what will be the green ones I can delete. And the restriction is just, once you choose the purple one that you want to delete, just draw this region. So this is like the region, say, determined by this purple path I want to delete. Once you draw that region, you have a bunch of green ones. Choose any of them. So basically the restriction is, do not choose green labels that are outside that region. As long as you choose green labels that are within that region, you are safe. You will build something that is a quotient of the given one. So in this case, if I choose 11 and 8, I can then build a lattice path matrix that do not have 11 and 8 as upper and lower path, but the rest of them it does, and that gives you a quotient. And so this allows me to think of quotients of lattice path matrix on a given ground set in this way. So here on the right-hand side, you have all the lattice path matrix on the ground set 3. And so the poset relation is quotient again. And on the left-hand side is the poset I showed you a moment ago. On the left-hand side is the poset of all positroids on the same ground set. So the right-hand side one, is a subposet of this one. Okay? So how do these two compare? So on both of these posets, every maximal chain is a full flag of positroids. On the right-hand side is a full flag of lattice path matrix. And because I'm working only with positroids, it means that the underlying matrix in both situations are positroids. So they are points in the non-negative Grassmannian. However, the difference between the poset on the right-hand side and the left-hand side is that in the right-hand side, every maximal chain, so this is a full flag of certain positrates, can be realized simultaneously, and can be realized simultaneously in such a way that the top rows are a positrate. So I think this is related to your question, or maybe I misunderstood. And what I mean by that is that in the left-hand side, for instance, this label, this chain here with the red spots, is certainly a full flag of positrates, but you will not be able to find a 3x3 matrix such that the top rows are a positrate. That's not possible. Although each one of these pieces is representable by a matrix with non-negative maximal minors, you cannot find a 3x3 matrix such that the top rows the first row realizes this, the top two rows realizes this. It's not possible. Okay. So how do I know that actually for lattice path matrix the story is like that? So how do I know that actually a full flag of lattice path matrix is a point here? It's not by constructing a matrix. I do not know how to build a matrix that realizes a full flag of lattice path matrix. That's not the strategy. So let me tell you what the strategy is. And it's going to, it has to do with thinking of flags of matrix as polytopes. So how do we do that? When you have a flag matrix, you can build its flag matrix polytope just by taking the Minkowski sum of the summands of the components. And that gives you a polytope. And in this case, for each one of these maximal chains, each one of those polytopes will have as vertices a subset of the permutations on the set 1 up to 3, because you are taking a full flag. So on the left-hand side, you have each maximal chain corresponds to a maximal flag of lattice path matrix. And say, for instance, you take this leftmost flag. So that leftmost flag it has in rank 1, let's see which one is that one, is this one. So the leftmost flag it has these two constituents in the non-trivial ranks. And if you take the Minkowski sum of the polytopes corresponding to those matrices, you get this subpolytope of the permutahedron. So the subpolytope whose vertices are these ones. And you can do that with each maximal chain. So in this picture, you can see perhaps that every polytope that you draw when you are in particular working with full flags of lattice path matrix is such that its one skeleton is actually an interval in this poset. This poset is the Bruja order on permutations. It's just an order on permutations. But the point here is that it's not an accident that the polytopes coming from lattice path matrix are intervals in the Bruja order. So actually, that is the way of proving that full flags of lattice path matrix can be realized simultaneously by a matrix that is non-negative. So this is a result that uses Bruja interval polytopes as defined by Lauren Williams. And so basically the result there is that if you have a full flag of matrix on ground set N, that full flag matrix will be such that its polytope has as vertices permutations of the set 1 up to N. The question is that polytope such that its one skeleton is an interval in the Bruja order? If the answer is yes, it means that your polytope is known as a Bruja interval polytope. If the answer is no, it means your polytope is not a Bruja interval polytope. And the result of Lauren et al. Tells you that there is a bijective correspondence between Bruja interval polytopes and full flags of matrix that come from points in the non-negative flag variety. So in our case, every flag of lattice path matrix, every full flag of lattice path matrix is such that its polytope is actually an interval in the Bruja order. Hence, each lattice path flag matrix comes from a point in the non-negative flag variety. So there is it can be found a common realization of all of them, non-negative. Okay? Okay, so as a particular example again, so here is a full flag, is a polytope corresponding to a flag of LPMs, and here is another one. And these two polytopes actually subdivide the permutahedron, but actually this subdivision is regular. So after studying full flags of lattice path matrix, I wanted to see if there was a subdivision of the permutahedron into flags of lattice path matrix. So where is a better context of this? So let's go back a little bit and let's recap on the hypersimplex Kn. So that's the hypersimplex Kn is the polytope of the uniform matrix Kn. And a result of Lukovsky, Parisi, and Williams tells you the following, that if you take a point in the positive part of the tropical Grassmannian Kn, that point is a tuple. So if you think of that tuple as heights in the vertices of your hypersimplex, then you are going to have a subdivision so that each piece in the subdivision is a positroid. And actually, it is an only if. It is an if and only if. If you subdivide the hypersimplex so that each piece is a positroid, then that subdivision is regular, and the heights are a point in the tropicalization, in the positive tropicalization of the Grassmannian. So here is the hypersimplex 2,4. This hypersimplex has 3 matroidal subdivisions, so 3 subdivisions so that each piece is a matrix. But out of those 3 subdivisions, only 2 happen to be positroidal. So only 2 of those 3 subdivisions happen to be that each piece is a positroid. Out of those 2 subdivisions, only 1 happens to have as pieces only LPMs. So now let's bring that parallel result to see if we can say anything in the case of the permutahedron. Because what is the permutahedron? The permutahedron is the flag polytope of the uniform flag, of the flag of uniform matrix. That's the permutahedron, okay? And so a result by Josvik, Loh, Luber, Olarte, and also almost simultaneously by Boretsky, Eyre, and Williams is the analogous of this, and is that say you take a point that is in the positive tropicalization of the flag variety, that's a tuple, and you think of that tuple as heights on the permutahedron. You take them as heights of the permutahedron and look at what is the regular subdivision. One direction of this result tells you that what you will obtain is a subdivision such that each piece is a flag of positroids, and actually the other direction is also true. So if you take the permutahedron and you subdivide it into pieces such that each piece is the polytope of a flag of positroids, then it must be the case that that regular subdivision is a point in the positive tropical flag variety. So the question is, are there subdivisions of the permutahedron such that each piece are exclusively flags of lattice path matrix? And the answer is yes. And so in the 10 minutes I have left, I want to show you how to start building them up. So because I do not do tropical geometry, so I cannot build them. I cannot build these regular subdivisions as tuples living in the positive tropical flag variety. I have to come up with another way of building them. And that other way of building them is by cutting the permutahedron into hyperplanes. So here, let me show you a couple of examples. In each one of these, I'm cutting the permutahedron n equal 4 with, in each case, with 3 different hyperplanes. And after, say, for instance, you take this one here. This one here is subdivided into 2 pieces. If you take this piece here, it will be actually the case that this piece here is an interval in the Bruja order. It's the interval that goes from the identity to 4, 2, 1, 3. And this piece here is another interval in the Bruja order. And the same happens with each one of them. So every cutting of each of these hyperplanes here is such that the pieces it gives rise to is an interval in the Bruja order, and it means that each subdivision is regular, and I can come up with heights such that those heights are a point in the positive tropical flag variety. And you can, so these ones are very coarse, right? It's just cutting, throwing a hyperplane, and it gives you rise to 2 pieces. But in principle, I was interested in the finest subdivisions into LPMs. So here is a refinement of all of them that gives you rise to this subdivision. And so here is a result, and it tells you that basically there are, say, 3 types of hyperplanes that gives you a non-trivial coarsest subdivision of the permutahedron into lattice path flag matrix. So these are hyperplanes, like the first one is just a hyperplane that tells you x1 is equal to I, where I is anything here, or xn is equal to I, either of those hyperplanes. The type 2 hyperplane tells you that x1 plus x2 is equal to 4, or this thing. And the last one tells you that xn minus 1 plus xn is equal to either 4 or this. So either of those hyperplanes, if you throw one of them into the permutahedron, will split it into 2 pieces, and each piece will be a polytope of a full flag of lattice path matrix. And so let me show you here the whole picture of the subdivisions of the permutahedron n equal 4 using this result. So for n equal 4, the hyperplanes that you can, the coarsest non-trivial subdivision that you can obtain of the permutahedron into pieces that are lattice path flag matrix are in the bottom. So they are indexed by those hyperplanes I just showed you. And then you can start asking yourself, can I throw a pair of them simultaneously and obtain, again, lattice path flag matrix? So here, this is the second level of the picture, the ones that are, say, let's call them compatible, okay? And in the top level is the finest subdivision of the permutahedron into pieces that are lattice path flag matrix. So that's how it looks like for n equal 4. And there are a lot of nice stuff happening around the subdivisions into LPMs. So one other thing that this result is saying here is basically that using duality of matrix, so if you have a flag of matrix and you dualize each piece, the dualization gives you another quotient. So this result is basically about dualizing matrix. And it tells you that basically this subdivision here can be obtained by dualizing this one here. So there is a lot of stuff around that going on. But this is something very recent I'm doing, so I have more questions than answers. So one thing that popped up was that some of the subdivisions that you can do in the n permutahedron can be obtained or give rise to some subdivisions of the n-1 permutahedron by deletion of elements. And so I would like to understand if all the hyperplane splits of the permutahedron actually can be thought of in terms of operations of the matrix appearing in each component. But let me go back here. Let me go here to this last question. So I showed you these hyperplane subdivisions of the permutahedron. That gives you the coarsest you can have. And that actually gives you the coarsest you can have among all the subdivisions of the permutahedron into pieces that are flags of positroids. So the lattice path flag matrix gives you the coarsest. I still don't understand the whole refinement of the picture. So I would like to know what collections of hyperplanes are compatible in the sense I described. Perhaps this question is, what are the F vectors of this subdivision, which is related to what Alex was telling us in his talk. And that I don't know either. But this table here is a table from this paper. And in that table, so they computed the F vectors of all the subdivisions of the n=4 permutahedron that are coarses non-trivial into pieces that are flags of positroids. So these ones are subdivisions, are coarses subdivisions into pieces that are flags of positroids. But out of all of them, these are the ones whose pieces are flags of lattice path matrix. And I don't know, in general, how many pieces there are in each one of those subdivisions. And as I said, I constructed these subdivisions by hyperplane splits, not by points in the positive tropical flag variety. So I would like to understand and bring all of this to the tropicalization of the flag variety. And so this last picture, just to give you more context to it, so in the paper of Boretsky, Williams, and Error that I just told you about, so they describe this fine structure on the positive tropical flag variety n=4. And this fine structure has 14 maximal cones and 9 rays. The 9 rays are these 9 coarsest subdivisions. And the way that the lattice path flag matrix subdivisions fit into that picture is like this. So there are 2 finest ones that correspond to these 2 maximal cones. There are 6 rays that correspond to these 6 hyperplanes, and there are some other incidents here. So it will be nice to understand how these subdivision into LPFMs fall into the whole fine structure of the positive tropical flag variety. So I just want to say that I use GitHub that Kris provided to me in their computations they did with Grobner basis of the ideal that they used to tropicalize the flag variety. And as I'm saying, I'm not a tropical geometer, but I'm trying to learn from Johannes, who has been very kind to share his knowledge with me. And these are some of my co-authors in these papers I have been working on. So, muito obrigado. Gracias.